In this video, we're going to investigate a couple more applications of linear systems. So as already noted before, linear systems come up a lot in real-world problem solving and also in other math courses. A natural question is thus, how can I tell whether I can solve an application problem using a system of equations? Well, there's sort of two questions you have to ask yourself, and if the answer is yes to either of these questions, then the answer is yes, you can probably solve it using a system of equations. So the first question you should ask is, does the problem involve more than one unknown quantity? If the answer is yes, then you can probably solve it with a system of equations. The second question you should ask yourself is, are there two or more equations or really conditions that need to be satisfied? Again, if the answer is yes to this, then you can probably solve it with a system of equations. So for example, and I'm going to apologize because this sounds dreadfully close to the two trains leave a certain place going in certain directions, you know? But it's not quite the same. So, an airplane flying into a headwind travels the 2,000-mile flying distance between Tallahassee, Florida and Los Angeles, California in 4 hours and 24 minutes. On the return flight, the airplane travels the distance in 4 hours. Find the airspeed of the plane and the speed of the wind, assuming that both remain constant. Here, we actually have two unknowns. So what are our unknowns that we want to find? Two unknowns. The first is airspeed of the plane. I'm going to write that, I'm going to denote that as P. And airspeed of the wind, which I'm going to denote as W. And then we also have two conditions. We know that one way, when you put the airspeed and the plane speed together, you end up going, it takes you more time than when you go back the other direction. And again, we're assuming P and W, these speeds are constant, okay? So what does that tell us? Well, here, the speed of the plane, when we actually do, so it's a 2,000-mile flying distance, okay? Here, I'm going to go ahead and, how do I want to do this? Let's do all of this in miles per hour. So let's do miles per hour in all of this, okay? First, I'm going to go ahead and convert some things. So 4 hours and 24 minutes. I want to write that in terms of hours first. That's going to be helpful. So when I do that, I get 4, so that's really 4 plus 24 over 60 hours. But that, if you do that, you end up with 4, so 24 divided by 60 is 0.4, so it's 4.4 here. So this is 4.4 hours. Good. Now, 4.4 hours, so what do we know? We know that it takes we know that the speed of the plane is plus the speed of the wind. So here, what's causing the idea here is you sort of need to see the picture. So in one direction, the wind's going to be going against the plane. The other, it's going to be going with the plane. And here, it takes longer when you fly towards Los Angeles. When one of the directions, it takes longer because the wind's blowing against you. So if I do P minus W, those speeds, that should be 2,000, the 2,000 miles divided by the 4.4 hours. On the other hand, the other direction is going to be, the wind is working with us, so it's speeding up the plane. We know we're able to do it that time in just 4 hours. Okay? Doing that out, you end up with 2,000 divided by 4.4 is a nasty, nasty number. So let's go ahead and multiply everything. I'm going to multiply everything by 4.4 and 4 on both sides. So I have, and actually, you can rewrite this. It takes a little bit of cleverness to do this. But if I multiply everything by 11, I actually end up with 11p minus 11w equals, here I will get 5,000. And here, if I multiply by 4, if I multiply everything by 10, I will get, or I can just do this, no, let's just do the division. So P plus W equals 500. Multiply everything by 11 here, so you end up with 11P minus 11W, 11P plus 11W, so those will get to go away. Here I would have 5,000. Here multiplying by 11, I get 5,500. And so once I do all of that out, I end up with 10,500. Not sure if you can see that there, but that's 10,500 there. And here those eliminate and I get 22p. Solving out for p, I end up with, I'm going up here because I ran out of room, sorry. P is equal to, it's 5250 divided by 11. But if you write that out, that's approximately 22.73. And then if you substitute in and get the other value, you'll end up with W is equal to 250 over 11, which is approximately 22.73. And these are both in miles per hour. This is actually 477.27. Now, go ahead and rework the last example with the first, where the return flight instead takes 4 hours and 6 minutes. On the count of 3, I'll reveal the solution. 1, 2, 3. So here we have to convert the hours and minutes into hours first. Then we set up our system of equations. We end up with these as our system of equations by multiplying everything here by 41 and everything here by 11. We end up with these systems of equations. To eliminate, we multiply the first by 11, the second by 41. The math is nasty here. Sorry about that. And we end up with being able to solve out for P and then using that to solve out for W. And now let's look, as our second example, let's look at an economics example. We have the demand and the supply equations for a video game console are P equal 180 minus 0.0001x, 90 minus 0.00002x, where P is the price per unit in dollars and X is the number of units. Let's find the equilibrium point for this market. Now, first, we need to define what we mean by equilibrium point. The equilibrium point is exactly where demand is equal to supply. Is equal to supply. Okay? So that's what the equilibrium point is. But, so what does that mean? Well, that means that really we're just saying these two things equal to each other. So we have 180, minus 0.00001x would equal 90 minus 0.00002x. So I'm just doing a simple substitution here. That's 180. Here, if we take that to the other side, we end up with 0.0000. So adding that 0.001x, because we're adding point, we are in a 1 to a 2. Let's go say it that way. Subtracting 90, you get 90 over here, which means x is equal to 90 divided by 0.00001, which is 9. So here we could use some exponents if we want to, but that's going to be 9, 1, 2, 3, 4, 5, 6, so 9 million. Okay? If you use that to solve for what P is in this scenario, Solving for what P is, we end up with P equals, and I did something not quite right. Sorry. This was supposed to be a plus in the original. So we have positive there, which means this is now a positive, which makes this a 3, which means x is actually 3 million. Either way, what are numbers anyways? Anyway, you end up with 3x equals 3 million. If you substitute that back into P, you would have, for P, you'd have 180 minus 0.00001 times, I'm using the first equation, times 3 million. I'll just write it. And if you actually calculate that out, you'll get $150 at the equilibrium point. So that's the perfect equilibrium price. And now it's time for you to try an example. So go ahead and find the equilibrium point for this model now with demand and supply equations given. On the count of 3, I will reveal the solution. 1, 2, 3. So here we have that the two equations will be equal once again. Solving out, we get 1.5 million for 1.5 million televisions, okay? And then that we have to sell to get to the equilibrium point. Once those are sold, though, you end up with $537 as the equilibrium price. For more practice in working some of these applications, be sure to see the textbook pages 487 and 488. In our next video, we will be talking about row echelon form for multivariable linear systems.